Yes, sir. Now it shows the screen.
Okay. Thank you very much for that nice introduction. The topic for today's presentation is antenna solutions for space-constrained Mimo communication system. So, as the title indicates, we are mainly going to focus on the aspect where if sufficient space is not there, how to allocate number of antennas in order to implement a MIMO communication system. Okay. So, what is the background of for this MIMO communication system? This is for a single input, single output system. That means if on the transmitter side you have one antenna, on the receiver side you have another single antenna, that is the CISO system. In that case, we already know from communication theory that the channel capacity is given by this channel criteria, right? So W is the frequency range, band of frequency. So from this equation, you can see that if you increase W, then the channel capacity can be enhanced, right? So if you see in last 1 decade or so, two specific methods were devised by communication engineers. One is the UWB communication, another is multiple input, multiple output communication technique. Okay. So from this equation, as you can see, if you increase W, the channel capacity can be enhanced. And using the ultra wideband concept, the data rate in a communication channel, wireless communication channel, was that can be enhanced to a larger extent. So that is one method, but today's focus is on MIMO systems. So MIMO system is another concept where you can enhance the data rate to a large extent. Okay. So we are mainly going to focus on this MIMO system today. So to start with, we are all familiar with this multipath propagation in a typical urban environment, right? If you have a transmitter placed at a specific point, and you have a receiver which is shown here as suppose the antenna placed on a car roof, then the receiver is receiving signals. If there is a direct path, if that is available from the transmitter to the receiver, it will get the direct signal from the transmitter. But in a typical urban environment, the signal that is coming from the transmitter is basically reaching to the receiver after multiple refractions. Okay? Because the area is too crowded, and you have many obstacles between the transmitter and receiver, so the receiving antenna is getting multiple signals. Okay. So because the receiver is receiving multiple signals, so if there is a variation in time of reaching of those signals from one signal to the other one, then that will lead to fading, right? What is the consequence? Because of this fading, you will have a variation in the signal to noise ratio. Specifically, If it is a moving object, if the receiver is planted on a moving object, you will get you can notice clearly that the signal strength is fluctuating to a large extent. Okay. Now, although we are saying that this is this multipath, because of this multipath propagation, you are getting multiple signals, and because of which you are having this fading, but this multiple input, multiple output concept, it is taking the advantage of this multipath channel. Okay. So let us see what are the different methods, because the whole idea is how to enhance the channel capacity, right? How to increase the bit rate, how to increase the data transmission speed. Okay. Now, what are the methods that are available? Right. You can transmit the data at different time slots, so that because of this time difference, they will not overlap with each other. Okay, so that is what is known as time diversity. Or you can send the data in different frequencies. So because of different frequencies, they will not again overlap with each other. So it may be in the form of different channels or techniques such as this spread spectrum or OFDM technique that will come under this frequency diversity technique. Okay, these two we already know from our basic communication idea. Besides these two diversity techniques, there is a third one that is basically used by this Mimo system. What is that one? That is what is known as space diversity, right? Space diversity is used as the basis for Mimo. Okay. So what exactly is this one? Multiple input. That means on the transmitter side you have multiple antennas. On the receiver side you should have also multiple antennas. So it uses antennas located in different positions to take advantage of the different radio paths that exist in a typical terrestrial environment. So although we are saying that the multipath environment is, because of this multipath environment, we are having fading, and that gives rise to the fluctuating SNR. But this Mimo concept, it takes the advantages of that multipath propagation, and because of which we can enhance the channel capacity. So what are the basics of this one? It's an acronym for multiple input, multiple output, widely known as Mimo concept. It's an antenna technology that is used both in transmitter and receiver equipment for wireless radio communication. And you can have various configurations of this Mimo system. For example, here in this diagram, you can see two transmitting antennas to receiving antennas. So it's a 2x2 Mimo system. Similarly, you can see in that device, it is using 4 different antennas. So you can have a 4x2 Mimo system or a 2x2 Mimo system, and so on, right? So the basic idea is instead of a single antenna on the transmitter side, single antenna on the receiver side, better you use multiple antennas. Now, what is the working principle of this Mimo concept? It takes the advantages of multipath, and it uses multiple antennas to send multiple parallel signals. Okay, so because you are sending the same signal through multiple antennas, so the receiver side, there should have a mechanism by which you can choose the or you can with the help of some processing technique, you should get the best out of all the transmitted signal, right? So the Mimo, with Mimo, the receiving end uses an algorithm or a special signal processing to sort out the multiple signals to produce one signal that has originally transmitted data, right? Because you are transmitting multiple parallel signals, so there should be some mechanism used on the receiver side to extract out the original data. Okay, now why this Mimo system is better as compared to a CISO system or single input, single output system? So as I told you, in a CISO system, the channel capacity, which is given by this particular formula, W, which is the bandwidth log 1 plus signal to noise ratio. Now, as far as Mimo channels are concerned, it uses the same power as that of CISO. You need not to use extra power to implement this Mimo concept. That is the first advantage of having this Mimo as compared to CISO. Second thing is the capacity, channel capacity, varies linearly with number of antennas, right? Because you are using multiple antennas on both sides, the channel capacity for the Mimo communication system, it increases linearly with the increase in number of antennas. This is a plot between number of antenna elements versus the channel capacity, right? So if you compare that with either a single input multiple output system or multiple input single output system, compared to that, the channel capacity for a Mimo system, it increases linearly with number of antenna elements. Okay, so that is about the basics of the multiple input, multiple output system. Now, this is one of the enabling technologies for the implementation of the 5G system, 5G communication system. So if you see, I've taken this particular diagram from this particular journal. To implement, to have a effective implementation of 5G, one of the technologies that is required is this massive MIMO technique, okay, or massive multiple input, multiple output technique. Besides the other things like antenna array beamforming, full duplex antennas, all those things, you need to have this particular thing, to have a complete 5G system, right? So, MIMO concept is one of the backbones of this 5G service. Okay, now coming to this 5G one, the realization of these high-level technologies brings about new challenges for the physical infrastructure designers that include the antenna microwave engineer. Because, see, all these technologies, whether it is for a microwave engineer or for a semiconductor engineer or for a communication engineer, everything has to be aligned as per the requirement of the 5G service, as per the requirement of the 5G service. So when I am saying that, what does it mean? That means because it is one of the enabling technologies is MIMO technique, we need to see that on both sides, on the transmitter side as well as the receiver side, how to fit multiple antennas to implement that 5G service. Okay. And that is the implementation of like fitting multiple antennas on both sides is not that easy. That we will see. So and as we know, in 5G we are going towards millimeter wave band. and in those millimeter wave bands, it encounters severe free space path loss, because of which you are having a degraded signal SINR, signal to interference plus noise ratio. So for that you need high gain antennas with directional beam, right? So that the wastage of power that is coming from the transmitting antenna should be as less as possible. Okay, or in other words, we need very directive antennas, Okay, so when you are we are saying that in 5G you need very directive antennas. What is the consequence of that one? A narrow beam provides only a limited spatial coverage, making it amenable to multi-user mobile streaming. So you can see the diagram in the base station. What happens in current 4G system? The base station antenna is covering. See, you can see 3 antennas to cover 180-degree area. So it is covering a large distance or large area. So all this with a single beam, it can cover the terminals available in that particular shaded area. Okay, but if you go to the 5G communication system, because you need very directive antennas, and if you have a directive antenna, then it can serve only a few number of devices, right, or few number of receiving antennas. So what is the solution for that one? You need antennas that are capable of producing multiple beams, right? So the multi-beam antennas, which are capable of generating a number of concurrent but independent directive beams with high gain value to cover predefined angular range. So what was having previously? It was creating a broad beam, and it was serving number of devices covering in that particular area. But because in 5G you need very directive antennas, so these antennas should have the capability of producing multiple beams. So if the base station antenna is capable of producing multiple beams, then depending on the requirement, it can communicate with specific users. Okay. So what exactly is happening in this particular case? See, as far as 5G is concerned, the theory says that all these individual beams should have independent control. That is first thing. Second thing is, see, depending on the position of the user, depending on if one user is far away from the base station and another user is suppose very near to the base station, so it should utilize minimum energy to reach to the nearby user, and it should use maximum energy to reach to the user which is far away. So that particular control should also, the antenna should have that particular control, right? So it not only it should have the capability of producing multiple beams, but it should also have the capability of controlling the beam power. Okay, and this is what is known as the key hardware for enabling massive MIMO technique. Okay, so the present 4G technology is going to replace by a system which is of this type, which is shown on the right hand side diagram. Okay, So in 5G, we are going to have a baseband antenna with capability of producing multiple very direct tube beams. Okay, so because it is having multiple antennas on both sides, transmitter side, receiver side, and let us see from the basic antenna theory how an array produces a specific direct tube beam. So the general from general antenna theory, we know that if a single antenna is capable of producing a or having a radiation pattern of this type, then by taking number of such type of single antennas, you can form an array of antenna, and each from the diagram center diagram, you can mark each antenna element is connected to a phase shifter and an attenuator. Okay, so by playing with these phase shifters and attenuators, you can produce a beam in any desired direction, right? So complete theory is available for that, how to find out the phases of this phase shifters and what should be the values of these attenuators, so that you can make a specific beam with a specific directivity in a particular direction. So that array theory is completely established one. Okay. So to make a beam in a specific direction, you fix the value of these phase shifters for the multiple antennas that are available in the array, and because of that phase difference between consecutive elements and the path difference of the different rays that are going towards the in a particular direction, because of that path difference, you are getting another phase difference, and both the phase difference, if they are meeting in phase, then you are getting a specific beam in a specified direction. So this is from the basic array theory, the concept how to make a beam in any desired direction for an array, and that concept is what is known as phased array concept. So because in Mimo system, you are using multiple antennas, so the same theory, array theory, that is applicable for any other array can also be applicable for the array that are available in Mimo systems. So if you compare the 5G system with the 4G system, 4G was using single user MIMO concept, but 5G will use multi-user MIMO system. And as I told you, each data stream received is independent of each other, independently by separate receivers. Okay, to transmit different power levels to different users, a multi-user MIMO scheme or beamforming is required, and there are techniques available how to create or how to get multiple beams from antennas. But as far as today's discussion is concerned, we are not going to discuss that particular part. Okay, how to have a multi-beam antenna. Okay. So another advantage that you are getting when you are creating a narrow beam or high directive beam, because if in a cellular communication system, if a particular user want to use the base station, then the base station creates a beam in that particular direction. But in the present system, the beam is a large angle beam. The beam width is very large, so it is basically wasting power in other directions, right? So instead of that, if you can have a narrow beam, then you can conserve that particular power also. Okay. Okay. So that is about the general Mimo system, Mimo concept, and how this Mimo system is going to change the scenario in the coming 5G communication system, right? So the basic idea is, instead of having single antennas on the transmitter receiver side, you need to have multiple antennas on both sides. Okay. So if that is the case, it has been found that the capacity can be enhanced to a large extent, right? Or in other words, the data rate can be enhanced to a large extent, right? Okay. So what are the challenges? Because the concept of Mimo was conceived by the communication engineers, right? And when as an antenna engineer, when you are going to implement that, right, then you will find that there are a number of challenges that has to be faced in order to completely implement from a 5G system. If you see from antenna engineer's point of view, we are not discussing what are the challenges faced by a microelectronics engineer or a VLSI engineer or a communication engineer. So basically, today's discussion is what are the challenges that is to be faced by a antenna engineer for a successful implementation of this Mimo concept. So first thing is, in a cellular system, on the base station side, you have enough space, so you can use multiple antennas without any difficulty, right? You have sufficient space, and by taking the concepts of the array theory, you keep the antennas at specific positions, you make that particular array, and you can implement that one. That is first thing. Okay. Now coming to the other side, the user side, we are discussing the cellular communication system. So on the user side, because I have a small I'm getting a background sound. So, but if you see on the receiver side, the user side, I have a very small device, right?
So pardon me,
Sorry?
sir, your slides is not changing.
Where are you now at present? Which particular slide?
Antenna solutions for Mimo system, communication system here.
Yeah, I am discussing that one only.
Okay. I think you were telling that. Okay.
Is it in full screen mode now?
Yes, sir.
Okay. Okay, let me first discuss, then we will go to the slides, right? So if you see from user side, I have a very small device, but to implement that Mimo concept, I need to fix number of antennas inside that small device. Okay. It is very difficult to fit a single antenna. Now I have to fit multiple antennas in that small device. Okay. that is the biggest challenge as far as the implementation of MIMO concept in cellular system that we are going to discuss today. Okay. Second thing is, see, as per theory, like when the MIMO concept, if you see all the communication related papers on MIMO, you will find that the communication engineers they have developed the theory by taking the antenna as a isolated isotropic antenna. Although these are multiple antennas on both sides, but they have assumed that these are all isotropic antennas. These are all separate individual, there is no coupling between these antennas. But when you are trying to implement that as an engineer, if you we know that if you keep two antennas close to each other, you will find some mutual coupling. So once you have mutual coupling, it will not give you the 100% that you are expecting from a MIMO system, right? So these are the challenges for an antenna engineer for the effective implementation of 5G. Okay. So let us see how to tackle this particular problem. What is that problem? In a space constraint system, because in a small cell device you don't have sufficient space, or for that matter in any device where you are not having sufficient space to fix those multiple antennas for the effective implementation of MIMO communication system, then what to do as an antenna engineer, how to solve that particular problem, right? There we need to use a concept what is known as antenna diversity. What is that? It's a communication method that takes the advantage of multiple antennas, a transmitter or receiver side, to capture statistically independent copies of transmitted signal. Okay. What is that? Let us see this this particular diagram. Suppose you have a two antenna element MIMO system, right? What is that? There are two antennas, right? Two different antennas, and from the basic array theory or from basic antenna theory, we know that the minimum separation between these two antennas should be lambda g over 2. Okay. So when I'm going to implement this two antenna element MIMO system, I need to give a separate feeding to antenna 1, a separate feeding to antenna 2. Okay. So if you have space for fixing these antennas, placing two separate antennas, no doubt you can do that, right? Without any hesitation you can do that. But the problem is not that one. Problem is, because I don't have any enough space to place multiple antennas, then what I can do is I will keep one antenna only, right? But I will give two different feedings to these antennas in such a way so that although physically this is a single antenna, effectively it will act as two different antennas. Because space is a constraint, so I can fix a single antenna with two feed points, but I need to devise a technique where although physically a single antenna, effectively it will act as a two antenna element system. Okay, let us see how to implement that one. You can have this single antenna. Suppose with the help of this two feeding, suppose it is producing patterns which are patterns in orthogonal direction, right? One in forward direction, suppose another in the suppose in 0-degree direction, another is in 90-degree direction. So these two radiations, they will not overlap each other because the radiation patterns are not overlapping. So if you are trying to send the data with the help of these two patterns, they will not overlap because these two are going in two different directions. Second thing is you can use a polarization diversity also. What is that? We know that even if two signals are of same frequency, but if they are having orthogonal polarizations, they will not overlap with each other. For example, if one is having a left-handed circularly polarized one and another is producing right-handed circularly polarized wave, Lscp and Rscp, they will not overlap with each other. Or you can have a combination of these two, pattern as well as polarization. So in this diagram, you can see that the transmitting antenna is capable of producing two different polarizations. One is in clockwise direction, another is anti-clockwise direction. And with the help of these two polarizations, you can send the signal in the same frequency, and they will not overlap with each other. That much we know from the general electromagnetics. Okay, so these diversity concepts has to be used so that a single antenna can act as multiple antennas. Let us see an example of this one. So we have implemented this. The specified goals. Main thing to see is that means the single antenna should have the capability of producing both Lscp and Rscp. So if you see, all these antennas are planar antenna structures, and you can see that to get a circularly polarized signal, the most widely used method is the corner truncation method, corner cut method. So on the radiating patch, you can see that these two corners are cut, okay, to get circularly polarized signal. Now this is one feed connected. You can mark the feed port. Okay. This is when you are activating, exciting this particular feed port, then the antenna will give you a specific circularly polarized signal. And you can mark the feed also at this point. At this point, you can mark the feed. It's a gap coupled feed. Okay, over the coaxial feed, we prefer to use the gap coupled feed. Then the feed is not a conventional feed; it's a L type of feed, right? And by choosing specific length for L1 and L2. You can create a specific circularly polarized signal. Okay. Then exactly in the other similar way, we attached a second feed, feed point 2, and in the similar way, right? And again, you adjust these lengths so that it can produce the circularly polarized one. Now, if you see the feed port 1, it produces an electric field E1X, E1Y, and similarly feed port 2, it produces electric field in this and this directions, right? So these two, E2X and this E1X, these two will cancel out, and you will get the effect of this Y-directed fields, okay? Now, because of this feeding, this specific type of feeding, one port, if it is producing the Rscp, the other port will produce Lscp signal. Okay. So let us see what are the different type of couplings that will come, because you have excited a single antenna with the two feeds, and the two feeds are placed very close to each other, right? So the coupling between the two excitations, it can be controlled by two physical mechanisms. One is the coupling of radiated fields, right? The radiated field coming from feed because of feed port 1 and feed port 2, they will try to couple each other. But in this particular case, because one is Lscp, another is Rscp, they will not couple. What is the second mechanism because of which you are going to get coupling? Coupling of induced surface current components. Okay. So, because of Lscp, Rscp, the radiated component will not overlap. So only component that will contribute to this coupling is your surface current coupling. Okay. So in order to have, as per theory, in order to have a effective implementation of this Mimo concept, these two should have zero coupling, right? These two ports should have zero coupling. Okay. So in order to reduce this coupling, that is in this particular case that is coming from surface currents. Let us see what are the methods available to reduce this coupling or to have a isolation between these two ports. These are here I have listed out the isolation enhancement techniques that are available in the literature. What are these techniques? You can use slits or slots, right, in between two antennas. You can see two monopoles. In between that, you have slots and slits to reduce the mutual coupling or to enhance the isolation. You can use metamaterials. You can mark the presence of metamaterials in between these two antennas to reduce the coupling. Then another method is you can use a neutralization line to enhance the isolation, or parasitic elements can also be used to enhance the isolation between two consecutive antennas, right? Now, if you see all these isolation enhancement techniques, in all cases, you will find that in order to place that this isolation enhancement method, to place that one, you need another extra space, right? Everywhere you need extra space to place that particular component, whether it is parasitic or metamaterial. But now here we are discussing the case if no space is available, or there is a no sufficient space is available, how to implement the Mimo technique. Now, if I go for these isolation enhancement techniques, here I need extra space to place those extra elements, right? So instead of going for this traditional isolation enhancement technique, what we did in our case, this was our antenna, and we found that when we observed the S parameters, this is for S21, right? Coupling between port 1 and port 2, we found a tight coupling between these two ports, right? So what we did is the idea is to use a lossless decoupling network at specific distance from the antenna ports where the equivalent mutual impedance is purely imaginary. So this is one port, this is another port. If you go from one port to the other port, you will find at certain point the mutual impedance is purely imaginary. So the idea is, if at that particular point where it is purely imaginary, if it is completely capacitive, use an inductor of that specific value. If it is completely inductive, use a capacitor of that specific value. That is the basic idea, in order to neutralize that particular value. Okay. So introducing the decoupling network, a phase quadrature is achieved between the two ports that lowered the coupling, right? So at this particular point, while moving from one port to the other port, in this decoupling network, we used at this point an inductor of 1.2 nanofarad. Because of the presence of this inductor neutralizes the capacitance that is available at this particular point. Because of that, you can now see there is a drop in the mutual coupling value, right? So this is without the decoupling network. This is with the decoupling network. Okay. So now because you can mark there is a large isolation between these two ports, right? First thing is the radiated fields are not coupled because one is producing Lscp, another is producing Rscp, and as far as the surface currents are concerned, we used a specific value of inductor to reduce that surface coupling effect. Okay. So now this particular antenna can be used as if it is a two-element antenna system, right? So these are the design details of the antenna that you can see from the publication. So this is the fabricated antenna structure, and the parameters were optimized for the antenna to work at specific frequencies. Okay. And we have observed the axial ratios also for the two ports to verify whether they are actually producing the circularly polarized waves or not. Then the current distribution was observed to see that it is actually one is actually producing Lscp port 2 and the port 1 is producing Rscp. This is animation, but at present I don't have that animation. Actually, you can see that one is moving in clockwise direction, another is moving in anti-clockwise direction. Then after designing and implementing the antenna, then we tested it, the antenna for its other parameters. These are the radiation pattern gain. We're not discussing that in detail. Then to see whether it is actually fit for the implementation of MIMO concept or not, we tested its envelope correlation coefficient and total active reflection coefficient. Okay, you can find the details of this from the MIMO theory, and we found that both these coefficients are satisfying the criteria that is required for implementation of MIMO concept. Then we compared the effectiveness of our antenna with the other similar available antenna structures. Then you can find that the complexity is very less. Okay, but at the same time it is applicable for implementation of MIMO concept, although physically it is a single antenna. So the conclusion from this particular design is it is compact, that means single radiator supporting both Lscp, Rscp, and the antenna can be used for full duplex applications. Okay, let us see one more structure of the use of pattern and polarization diversity concept. Now you can see again it's a planar antenna structure. The gray marks are the metal ones, and the blue portion are the substrate portion. This is the front view of the antenna. This is the back view of the antenna, meaning on a PCB sheet, on a single PCB sheet, on the upper side this particular thing was printed, on the lower side this particular thing was printed. Okay, what does it mean? That means the separation distance between these two antennas is the height of the substrate, right? So these two antennas are this much closely placed, right? So while it's quite natural that because as per theory we know that the minimum distance between two antennas should be lambda by 2, but here these two antennas are separated by a distance which is the height of the PCB sheet, right? On two sides of the PCB sheet, these two antennas are printed. Okay, let us see how they are behaving. So here we have used both the pattern as well as polarization diversity concept, right? In the previous case, we have used only the polarization diversity concept. One was creating the Lscp, other was Rscp. But here it's a mix of pattern as well as polarization diversity. What is that? As far as pattern diversity is concerned, this antenna, which is printed on the top surface of the PCB sheet, it's a broadside radiator. It's a broadside radiator, right? Whereas the bottom side antenna, it is a end fire radiator. It is radiating in this particular direction. Okay, it is a broadside radiator, and this one is an end fire radiator. Okay, so these two patterns are not overlapping with each other. These two patterns are not overlapping with each other. Okay. As far as polarization is concerned, no doubt this is giving a circularly polarized signal, but this one is giving a linearly polarized signal. Okay. So as we know, the circularly polarized signal is having both a horizontal as well as a vertical portion. So the one part of that circularly polarized signal may interfere with this the linear polarization that we are getting from the other antenna, which is printed on the back side of the PCB sheet. But because the the patterns are not overlapping. Because the patterns are not overlapping, so that's why the coupling that you are going to get between one component of that circular polarization and the component of this linear polarization will be very, very less. Okay. So I'm not going to the design details of this antenna. These are the design parameters, the design dimensions, and this particular thing, the first radiator was optimized to give a circularly polarized signal. Okay. Now the feeding port for the upper radiator is along this side, whereas the feeding port for the lower radiator is along this side. Okay. And after simulating the structure, we verified its performance. Then you can see that from the axial ratio 1, we can mark that it is producing that circularly polarized one, and here you can mark the S11 plot. You can mark the one is black one is S11 and the blue one is S21, the coupling between the two ports, and the red one for the second port. Okay. And you can mark that for the radiation pattern. This is the in the background. You can see the antenna. Now see, you can mark the placement of this lower antenna, which is exactly below, placed exactly below the upper antenna. Okay. Now in one case, for the broadside radiator, it is radiating in this side, whereas for the other radiator, it is radiating in the end fire direction. Is as if that is radiating just like a horn antenna. Okay. And you can mark that this is the fabricated prototype, and we found that for both these ports, or for both the excitations, we are getting sufficient amount of gain. So the idea is, although in previous case you have used one type of diversity, you can use multiple diversity techniques to get extra benefit from the antenna. What does it mean? See, in this case, in the second example, you have two different patterns and two different polarizations, right? Or in other words, now you have four parameters. Now you have four parameters that you can play with to transmit the bit stream or to transmit the data, right? So in the previous case, you are having only two parameters. Now you are having four different parameters, two for the pattern and another two for the polarization. Okay. So you can see, you can find the details of these two antenna structures that we discussed, where the pattern and polarization diversity techniques can be used for solving the problem of implementing Mimo antenna in a space constrained environment. The details that you can find in these two publications. Not only that, if you study the literature, you will find other antennas having or that have used a similar kind of concept. So all those antenna structures, all those antenna concepts, and different diversity techniques are compiled in the form of a book, and this is compact antennas for high data rate communication. But this particular book, it contains the discussion both on UWB and Mimo on technology. So you can go through this the content of this particular book, and you can order a copy for your library also. Okay, so this book contains we discussed only 2 varieties of antennas, and in this book you will find the other varieties of antennas using this type of concept. Okay. Thank you very much for your patience hearing. If there are any questions, I will be happy to answer that.
Okay, thank you, sir. If there are any questions are there, please. Yes, sir, I'm taking the questions.
Yeah.
So the first question is, kindly give some insight about importance of angle of arrival and angle of departure in 5G beamforming.
See, that particular, the angle of arrival thing is more towards communication than antennas. But as I told you, in a phased array concept, you can move the beam in any direction, and that can be implemented with the help of the phase excitations of, by controlling the phase excitation of individual elements, you can make a beam in any specific direction. Suppose we are not going to the signal processing part. I am discussing it from antenna point of view. Suppose at the receiver point, you got to know that a signal is coming from theta equal to 30° direction. So you need to move the beam of your receiving antenna or receiving array in 30° direction, right? Then only you can get maximum signal at your receiver point, right? So, to make a beam in a 30° direction, you need to find out what are the excitations I need to fix for the individual antenna elements. And in array theory, from any antenna book, you will find that how to choose these excitations.
Okay, thank you, sir. The next question is, kindly elaborate single user MIMO.
Okay. See, in single user MIMO concept, you have a single base station, and that is communicating to a single user, okay, a specific receiving device, right? Now, what exactly is happening? The base station processing for this single user MIMO, as far as 4G is concerned, is not different from a other user which is present in that particular coverage area. But as far as 5G is concerned, each directive beam is individually controlled. That means a directive beam which is connected to a specific device is individually controlled by the base stations. Or in other words, the complexity of the signal processing burden on the base station particularly in 5G, is very high. Why? Because it has to control because each user is having a MIMO antenna in their device, right? So, but the controlling is individual. So that's why that is called multi-user MIMO, and this is called single-user MIMO. You are not audible.
Okay, sir. The next question is, the meander lines can also be used, or it is same as the neutralization line?
Yeah, basically the concept is almost same. Meander line and the neutralization line, the concept is same.
Okay, thank you, sir. Next question is, sir, can we say multi-beam satellite communication is having same concept that of Mimo concept?
No, it's see, you have to have extra things for the antenna to be capable of producing multiple beams. There are techniques available. You can find that in literature. There are techniques available. That means you can use a lens, suppose you have a reflector at the focus point of the reflector. Instead of a single horn, you use multiple horns, so that you can create multiple beams, right? So you need extra components to create multiple beams from the antenna. It's not the same thing.
Okay, thank you.
But if you see from array point of view, the array that means you need to make the extra arrangement in such a way so that the array, instead of producing a single beam, it can produce multiple beams, right?
Okay. Okay, thank you, sir. So next question is, how do we know location where impedance is imaginary?
Okay, that is by trial error method. You start from one port. It's a metallic line connected between these two, right? At each and every point, like you divide it into number of subdivisions, and each subdivision you check what is the impedance, right? Where you are getting the impedance which is basically imaginary, there you try to attack with a opposite element. That is by trial error method only you need to check.
Okay, thank you, sir. So next question is, for a full duplex system, what is the minimum isolation required?
See, first thing is, for a full duplex system, all the isolation is not coming from antenna part, right? There are other circuitry that is available on the transmitter side or the receiver side, in the receiver transmitter chain or the receiver chain. Every component of that transmitter chain is contributing to the isolation. So the isolation that is coming from antenna part is just a small portion. But if it is more than 30 dB, basically as far as antennas are concerned, in antenna case, I have seen people have achieved up to 30 dB isolation only with the help of antennas. 30 dB isolations, I have seen.
Okay, thank you, sir. Next question is, how does the polarization diversity antenna work in practical?
See, the basic theory of electromagnetics, it says that Lscp will not overlap with Rscp, right? Even if the two frequencies are same. Now, if you see the antenna, the structure that we have discussed, see there are two excitation ports, that means two feedings. So both the feedings are of same frequency, right? The frequency is same, but one is producing Lscp, the other one is producing Rscp, right? So both the through these two input ports, you can send data separately without overlapping. That is the idea. Without overlapping, you can send the data. See, another methods that instead of using the same frequency, you can use two different frequency, one for two different frequency to send different data type. But in that case, you need large frequency range. But in this case, with same frequency range, you are trying to send the signal, but at the same time without overlapping. Without overlapping, that is important.
Okay, sir. Thank you. So next question is, how can we validate the results of Lscp and Rscp in circularly polarized antenna?
One is in simulation level, you check what type of polarization you are getting. Second thing is you need to check, even if you are getting in simulation, you are getting perfect result, it is not sure that in measurement you are going to get the same thing. So you need to measure the polarization of the antenna by exciting the two ports individually, right? So how to do that? Take your transmitting antenna as the circularly polarized antenna, and the receiving antenna you can take as a linear antenna. Okay, the basic method is this one. So as you know, a horizontally placed linear antenna will transmit horizontal polarized signal or receive horizontally polarized signal. Similarly, a vertically placed linear antenna will receive vertically polarized signal. So you gradually rotate that receiving antenna from 0 degree to 90 to 180 to 360, and at each position you mark what is the received signal. From that you can find out what is the polarization of the antenna.
Okay, thank you. So next question is asked by Mr. Chandravir Singh. Suggest some new topics for PhD in antenna systems.
You come for PhD, then I will tell you. As far as one thing you can try nowadays, the buzzword is the full duplex antennas, right? Yeah. Full duplex antenna is that is required for 5G, and most of the research nowadays are focused towards this in-band full duplex antennas. That means in the same frequency range, it should work as a full duplex antenna. Same frequency for transmission as well as for reception.
Okay. And the last question is ECC used to characterize polarization diversity in Mimo, or any other parameter is used?
Come again? Again the question, please.
Is ECC is used to characterize polarization diversity in Mimo, or any other parameter is used?
Yeah, that the parameter, these two different parameters are there for characterizing the Mimo. One is that envelope correlation coefficient. Yeah, the ECC can be used to characterize that one. The question is it applicable only for Mimo or what?
Yes, sir.
Yeah, for Mimo, ECC can be used for checking whether it is suitable or not.
Okay, and the one more last question is there. Will the number of beams be equal to the number of users in a cellular cell in terrestrial Mimo?
Particularly in Mimo, like the implementation of 5G Mimo, see, depending on the requirement, the base station will produce a beam in the specific direction. It's not that you have a broad beam and it will cater the need of all the devices that are coming in that particular range. The user, when it is requesting, then depending on the requirement, the base station will take a decision to form a beam in a specific direction.
Okay, thank you, sir. I think all the questions has been answered. And thank you, participants. Thank you, Professor Amalendu Patnaik, sir, for such a vibrant talk, starting from the basics of Mimo, everything. You have covered so many things, and given the insight to the researchers for doing the work in this field. And I also would like to thank the IEEE Rajasthan subsection, Antenna Propagation Society Chapter Jaipur, and IEEE Young Professional Affinity Group Bangalore section for just giving the opportunity to arrange this workshop for the participants. Thank you, sir. Thank you, sir, for giving your valuable time.
Thank you. Thank you very much.
Thank you, sir.
So I am logging out now.
Okay. Thank you, sir.
Okay then. Bye.